morning, everyone. My name is Jasmine Prieto. My mentors are Neil Reyes, and in this talk, I'll show you how we could use NMR as a thermometer for low temperatures. Studying physical phenomena at low temperatures is imperative for a complete understanding of condensed matter systems. An example of this is superconductivity. Therefore, it's important to accurately measure at low temperatures, and this is typically done using sensors. Most sensors are dependent on field and aren't very accurate at low temperatures. So, how can we improve accuracy and precision at low temperatures? We could use NMR as a thermometer. This is based on the Kringle relation, which is given by these two expressions. And what's important here is that it depends on fundamental constants. For example, one of these constants is gamma n, the gyromagnetic ratio of the specific nucleus we are using as a probe of temperature. Since everything except T1T is constant, these expressions simplify to T1T equals a constant for any simple metal. It's our goal to find this constant because it's the basis of NMR thermometry. So, for copper-63, T1T was measured by Anderson and Redfield in the late 1950s, where T1T equals 1.27 second Kelvin, from 0.01 to 0.1 Tesla at 1.1 Kelvin. So for our experiment, what we want to know is, to what extent is T1T field and temperature independent? So first we prepare the copper powder sample and we coat it with silicone grease, and then we make silver coils. We cool the sample to 4 Kelvin by flowing liquid helium, and then we cool down to 1.3 Kelvin by using the vacuum pump, which lowers the pressure. Since our sensor measures temperature by detecting changes in resistance, we must calibrate for magnetoresistance because it causes the resistance to change when a magnetic field is applied. So over here we have two graphs of the calibration that I made on origin, and we could see, for instance, that at 12 Tesla and for an actual temperature of 1.2 Kelvin, the apparent or measured temperature has more than 10% difference from the actual temperature. So its effects are stronger at higher fields and lower temperatures. Now we get to measure T1 from 1.36 to 4.25 Kelvin and from 7.8 to 12 Tesla. T1, the relaxation time, is defined as the time that it takes for the nuclear spins to recover to equilibrium following a disturbance. So we retrieve that value by integrating and fitting our FID. And what we found is that the average value that we got for T1T was 1.31 second Kelvin, which is larger than the previously determined 1.27 second Kelvin at lower fields. So we found NMR to be a viable measuring method for measuring temperature because we verified that it was temperature and field independent. So it's constant. Now, for example, if we look at our graph here, we could see that T1T barely changes with field or with temperature. Now, if we compare that with previous data, we could see that our T1T values are slightly larger, and this could be because they measured below 1 Tesla, whereas we measured above 7 Tesla. We also have modern technology 65 years later. So these findings can improve the precision of the instrumentation at the MagLab, which benefits the users. In the future, we would like to apply NMR thermometry to platinum-195 and thallium-205. We also want to take T1 measurements from 1 to 45 Tesla and below 1 Kelvin. And that's my presentation. Thank you very much. Thanks to the MagLab, thanks to Kwana, and special thanks for my mentor for guiding me and supporting me through this project.